Okay, this is acoustically odd. There's a second part of the announcement. So I only learned that the other speaker pulled out pretty much yesterday, which means that there's only a part one, but let's see how long that part one stretches. Also, I have the tendency to be, I don't know whether intentionally or unintentionally, but definitely controversial. Whenever you think something is going completely off the rails, just interrupt me. Okay. Then, Trees Oracle's explanations using ancient AI wisdom at to make sense of modern machine learning magic. Ancient in the sentence means 90s. Still, this is always an interesting representative poll. Who of you has read machine learning papers dating before the Jan LeCun, Benjo and Co. survey? So before 2012, hands up. Not that bad. Usually, this is way fewer people. But yes, the world didn't start with deep learning. There was some unordered stuff before. Anyway, thank you for the warm welcome. My current employer, usually lovingly called Alpha, in full called Telefonica Innovation Alpha, but then it doesn't sound as cool anymore, is Europe's first moonshot factory. What does that mean? That means that if you've ever heard about what's now called X, and in the olden days used to be called Google X, but then they became the X in the alphabet, has a European counterpart. And we are basically an entity in the Telefonica universe. We are our own entity, and we are tasked by Telefonica to go for high-risk, high-impact projects. There's 3 criteria. So we ought to address a huge problem, usually somehow aligned with the 28 United Nations Sustainable Development Goals. It should require breakthrough technology to solve it, where this means plausible tech. We don't reinvent things. We don't do, I don't know, beaming, transportation, Star Trek stuff. We take things which are proven to work on small scale, which are sufficiently scientifically proven to work. We build them, we scale them, we deploy them. And it should nonetheless be a radical solution, so it should be a game changer if we make it into it. Also, since, as I said, Telefonica Innovation Alpha, it should have something to do with what Telefonica is usually doing. Then, why are we called Alpha Health? Or why is the moonshot my team and I are living in called Alpha Health? Here, a bit of quick stats, and don't worry, we'll make it through this part of the talk very quickly. This is a plot of how healthcare spending has expanded in terms of GDP. So over the last 50 years, and it's actually continuing to go up, healthcare is a bigger and bigger market and is a bigger and bigger cost factor in also society budgets. Interestingly, if you have a look at how mortality rates develop, we clearly have made great advances since a century ago. Still, we are plateauing. Why are we plateauing? Well, one of the reasons you could give if you squeeze the data long enough is that we now kind of figured how to deal with infectious diseases, solutions like antibiotics. But other than this, we didn't figure really much. So for a couple of conditions, we can care. But for the majority of what remains, namely chronic diseases, we are still very much at the beginning of curing them or of preventing them. Then, if you squeeze the data a little further, you figure that 70% of the graph you saw before, at least of the right end of the graph, actually is made up by chronic diseases, spanning through everything from mental disorders to autoimmune diseases to cancer, diabetes, strokes, heart attacks. And if you then squeeze this data in turn, lots of squeezing, you figure that, okay, 25% of these chronic diseases you actually have to discount for either genetic predisposition or for environmental factors. But 75% roundabout are either behaviorally caused or at least behaviorally controllable. So our lifestyle can either cause them, or changes in lifestyle can at least help to manage and keep them at bay. There is an ample body of research basically tying this to, however you count, between 5 and 10 core behaviors, including things as getting enough sleep, having healthy interpersonal relationships, having a bit of a look at substance abuse and medication usage. Things which technically all of us would want to be good at, but hardly anyone ever is, because I'm gonna start training tomorrow, and come February, I won't ever touch alcohol again. Usually lasts until, say, the 3rd. At least if 1 and 2 are Monday and Tuesday, because early in the week is really bad. So the idea behind that, and as I said, Telefonica Innovation Alpha is to try to go for personalized well-being support. Telefonica happens to deal in telecommunications. We have at around 450 million customers worldwide. Most of them by now have a smartphone. How many O2 clients are in this room? Excellent. This could have awfully failed now, but okay. Hello, welcome. Telefonica extends personalized greetings. Yeah, no, but so we have an interaction device which presumably we have a close tie to, and this interaction device is actually equipped with more computing power than people used 50 years ago to get a man to the moon and back. So why not leverage that and make good use of it? There's a couple of additional side conditions we want to apply, because one of the fair questions would be, well, if it's that easy, why didn't anyone else do it yet? And so you just want to become another, you insert the name of a big social network here? No, there is more to our mission. One of the things we also deeply believe in is that one can do behavior change and one can do well-being whilst keeping the user in control and whilst being what, well, currently is fashionably called ethical. So this is part of the value proposition we want to test. Can we build tech which maintains control on the user side, and do users then actually also value that as an actionable feature? For us, that would mean we succeed, we get into the market, everyone is happy. For the world, it would mean that finally tech has become a little better. So, long story short, now cutting to AI. Within this context, we started building an AI lab, and the AI lab has 3 main missions, or 3 sub-teams, however you want to see it. One is what someone in the PR department or strategy department, which happens to be the same, called trustworthy AI, explainable artificial intelligence, explainable machine learning. So you want to be able to explain to your users why a recommendation was made, how it was made, and how the recommender works in the first place, because you're dabbling with their well-being. Empathic AI, in order to actually see whether your interventions work or in order to decide how to intervene, you have to have a pretty accurate picture of how your users are doing. And privacy-preserving AI, this now ties back to what I just meant with ethical. So ideally, we would be able to do all of that, deliver a highly personalized well-being assistant without ever seeing or touching the data. So keywords there are along the lines of secure enclaves on edge devices, are along the lines of homomorphic encrypted learning classification, you name it. And this is also the level of tech I meant when I said breakthrough tech, but plausible tech. So there are proofs of concept. It hasn't been scaled. It hasn't been deployed. But as we all know, there by now are TensorFlow libraries who allow you to do some of that. Microsoft has a pretty nifty suite for encrypted learning. The tech is theoretically around. Someone has to build it proper. OK, this was the intro. So, trees, oracles, explanations. We will focus on what the trustworthy AI team is currently doing, and more precisely on a bigger question which seems to be agitating the machine learning community and the AI community in general. I don't know who of you, I'm into polls today, who of you happened to be at last year's NIPS? Good, there was also someone. NIPS is this, well, it used to be a scientific conference. It's now one of the biggest industry fairs for AI and ML, where there's also a co-located scientific conference. And actually, interpretable, I think, was in the title of at least 3 of the workshops. And there's plenty of papers coming out in that space where people try to still do cutting-edge machine learning, or at least performing machine learning whilst being able to give the users or the regulators or whomever insight into what the model is doing. Why are we doing that? Well, the simple answer is because AI is currently being deployed. which in a way is the first time in history, so the field's been around at least since 1956. Still, big-scale deployment only started over the last 10 years. Yes, there were expert systems before, and sure, Mycin and all of it. Nonetheless, people having Alexas at home, people standing, looking somewhat oddly at Piccadilly Circus and talking to an etched box in their hand, all of this only came about over the last 10 years. Still, one of the main problems is, and many people or many users don't notice unless something went massively wrong, one of the main problems is that for most of the current performing tech, it's not entirely clear how it gets from its inputs to its outputs, which brings up questions on the liability side, but also questions on the, well, are we sure we are not discriminating against certain vulnerable groups? Are we sure everything is really going according to plan? Are we sure that in certain edge cases we are not causing catastrophe? All of these things. When people are talking about explanations, it's not clear what they mean. So if you've ever looked into the GDPR, this kind of laudable, ambitious, and, well, semi-thought through piece of European regulations on data privacy, you repeatedly have the mention of users or subjects of automated decision-making having the right to get meaningful insight into the logic underlying a decision. What that precisely means is still up for courts to interpret, but basically, if you're now running a big data analytics system in your bank, someone is rocking up there, they are filling in one of these questionnaires, the credit is rejected, the customer comes to the bank clerk and is like, why was my credit rejected? Then there currently is a fair chance, as I said, depending on how courts will decide once this becomes an actual issue, that the bank cannot say anymore because our statistical model says so. If this happens, the question is, what can we do? Either we quickly develop explanations, or we have to go back to linear regression, because there at least you could say what factors caused the decision. Now you can do a bit of mental math, how many Alexas will remain around. So, and then our personal note, if you're doing healthcare, it's only getting worse, because either you're dealing with a vulnerable group, or you're at risk of making people vulnerable. So if things go wrong proper. A bit of historic background, so don't worry, this is not going to be all talk, there will be formulae and stuff later, but to give you where we're coming from. People already discussed explainability once, and this is now when I say it in ancient times. So if you have a look at the expert system literature from the 90s or late 80s, people are looking into, okay, I have a long symbolic chain of things, how can I tell my user what actually caused the decision? And for example, if you are into fast trading systems, there's a fair chance that actually your system is not a trained neural network, but is a huge collection of handwritten rules. If condition A, then do B. If condition C, then do D. And your trading decision, or the system's trading decision, is caused usually by a conjunction of dozens or hundreds of rules. If you are in the banking sector, you currently already are liable. So if you sink someone's savings, people have the right to get an information on what happened there. And for all I've been told by a couple of colleagues working around the city here, it currently is enough if you just give the user a memory dump of all rules which were active at that point in time and tell them the truth is somewhere in there. Whether that's helpful is a different question, right? But at least if you read the GDPR and the appendix to it, it might not be enough anymore pretty soon. Why am I telling you about symbols? Because, well, at least people usually claim that what you're seeing on the left here, where you have, it's a family tree in disguise, but at least you have a structured representation with leaves and branches, is already better explainable than the signal chart on the right-hand side. This is the simple visualization. Whether it's enough as an explanation is a different question, but at least you're seeing structure, whilst on the right you're basically seeing wiggly lines. Funnily enough, even before the 90s, machine learning was around. It's surprising to some. But back then, machine learning was still much closer to the symbolic tradition. So what's nowadays called statistical relational learning, where people are learning from structured data, or where people are learning to come up with classifications over structured data, took its start there. And if you have a look at when Pat Langley and David Aha started the Journal of Machine Learning, they started on that. So in that context, a guy from the UK called Mickey actually came up with 3 different types of machine learning, or 3 criteria for how to name what you're doing when you're doing ML. In his view, it's written down in a workshop paper from the mid-90s, but it started in the late 80s. In his view, weak machine learning happens when a system generates an updated basis, building on sample data for improving its performance on subsequent data. So this applies to any kind of machine learning, hopefully, at least if your system works. If it's getting worse through training, then something is wrong. But he then was like, okay, what I currently get is an update, sample data, system performance improves over time. Then he was, but maybe I could actually say something about what's happening inside the system and not just pretend to be completely agnostic on input and output. So he defined strong machine learning as weak machine learning with the additional property that the system has the ability to communicate internal updates in an explicit symbolic form. So the system is writing out some symbolic information about what happened. How did the update cycle work? Still, it's only some symbolic form. It can be vectors, it can be logic gibberish, what have you. And then he defined UltraStrong machine learning, which is strong machine learning with the additional property that these updates are actually operationally effective, meaning that the user understands what happened during the update cycle and that the user can then interact in a better informed way. So there, all of a sudden, you have to provide insight into how the updates work, which the user can apply in providing either better training data on the next run if you're doing continuous learning, or knows better how to interact. And then we are talking what we understand as interpretable or as explainable AI and ML. You are actually informing a user. And I know this comes with a lot of other problems because not every user is similar and some people just know how gradient descent works. Most people don't. And you have to adapt the message presumably to each of them. But hey, Mickey, UltraStrong machine learning, paper I think in an EK workshop 1994, first mentioned late 80s. If you're having a look at what most, yeah.
Sorry, I didn't get what these updates could be, like the error or something like that?
For example, so something which characterizes the delta in your internal network state, or if it's a Bayesian network or whatever you're using there, the delta between t and t plus 1. Whatever you write out, errors would be my first guess. You could also just write out the differences in weight. Which of these gets you to ultra strong is a completely different question. But at least it will get you to strong. Most of current machine learning, so especially deep learning, is an incarnation of weak ML because nobody of us really cares about giving information about the updates as long as the system performance improves because we want to build systems which work. We don't care that much about how they do it as long as it's statistically valid that they do it. If we have doubts, we increase the size of the test base. Deep learning has another problem on that side, as at least the way it's usually applied, representation learning, where you don't have any control of what the representations in the intermediate network layers actually are. Then even if you would write out the updates, it might not be comprehensible in terms of human concepts. So sure, everyone thinks that this cute Google network, which first labeled cats on YouTube, first detects paws, then detects claws, then detects hairy. No, it doesn't. It's using what's most statistically informative at each layer in order to detect cats from non-cats. How would you now explain the internal layers? Question for a different day, maybe a different academic career.
Sorry, on that point,
yes.
You used visual representation
Yeah.
layer and then assigned a symbol to it. Would that be sufficient? So if you categorize each visual area?
Yes, but then the problem might be that the you can't refer to the characterizations. So you can refer to characterizations as long as we have concepts for it. You can refer to an edge. You can refer to a closed shape. You can refer to a paw. But what do you do if you actually have a, for our understanding, somewhat random collection of pixels across the image? So this is the problem with representation learning. Of course, what you could do is you could force the layers to correspond to meaningful concepts. And if there's anyone philosophically minded in the room, pardon my original sin here, but then you're already interfering. But yes, the idea is a step in the right direction. So if you then have a look at what people are currently usually presenting in these interpretable or explainable workshops, is one of the two. It's either comprehensible or interpretable. Interpretable meaning that you actually have a machine learning model which is mathematically accessible. People then usually tell me every machine learning model is mathematically accessible. Sure. But if you have an ultra-deep neural network, I challenge you to write me down that math formula and explain it to me in finite time. I know you can do it, but you'll run out of pen and paper long before we're there. Comprehensible systems for, say, classifying factory images of systems, which then tell you, well, there are halogen lights, there's a concrete floor, there are boxes, and there are machines. And then you as human cognizers make up the story that, yeah, okay, these are things you see in a factory, thus this is why it classified the image as factory. But this is a story you're making up. So you don't know unless you have insight into the systems working with these individual features, whether these really are the reasons for why it's at factory or whether it just detects that these things are also on there. And now we are talking Judea-Pearl, we're talking causality, we're talking modeling these relationships. Still also in its infancy. Nonetheless, if you're interested, the Book of Why, really good read. Making this a bit more tangible, one of the, as every analogy, somewhat odd, but actually quite fitting illustrations is the doctor analogy. So when a physician is talking to a patient, they usually are comprehensible models. Your physician is not telling you every test they ran on you. They're not giving you every blood value, every metabolic detail. They're just telling you, well, you have heightened body temperature, you're a bit yellow, and you've been traveling to an exotic country. I guess you contacted a fever affecting your liver. If they're talking to other doctors and medical staff, they don't bother about making up these features. They actually just use what is really happening. They're using the metabolic information, and the other staff is able to read it. So upper thing, comprehensible, lower thing, interpretable, but different target audiences. And as someone already mentioned, visual is one of the ways how we try to address this. So some of you might actually know that example. It's taken from the famous Lime paper, where one of the currently most popular local model agnostic interpretable machine learning frameworks was introduced. What Lime basically is doing, as are many other methods, more or less, is Lime is trying to give you for an input, which is then classified as pertaining to a category, say binary A or B, which were the most significant features or pixels for the classification. The simplest way how you can do that is by stupidly sitting down and flipping each pixel and having a look at how it impacts the output. More intelligent ways would, for example, look at how relevance propagates through layers. But the simplest thing is really sitting down, flipping pixels, checking whether your output label changes. What you're seeing here is from the Lime paper, and what they try to do is they try to learn a classification between dogs and wolves. It works smoothly, and this is one of the cases where it goes wrong, because the husky is classified as a wolf. Then they run the method, they look what were the most relevant parts of the picture for the classification, and this is what you see on the right. So this thing got the wolf label mostly because of the white stuff around the actual object of classification. And yes, in the 90s, the tank problem was an urban legend, but this one actually happened. So you, as humans, now can have a look at it and you recognize, yeah, well, heck, it's snow. Of course, wolves tend to live in snowy environments. Dogs usually don't, thus it learned this. Again, this is you making the interpretation. This is you being a doctor reading metabolic values. What can also happen, this is an example they actually engineered in that way. What can also happen is that you get 5 arbitrary places throughout the picture because the camera lens had a dirt speck there, because whatever. Still, this is current state of the art. There's a couple of more advanced things now, but the basic principle remains the same. The question now would be, so what about actual explanations? So if you go to someone and ask for an explanation, what they usually give you is one of these neat little narratives, which is adapted to what you actually know. So it's tying into your real-life environment. It's tying into your actual cognitive capacities. Can we cook up something like that? So we still have an image classifier. Can we maybe cook up something which either maintains the black box, but then we're still not entirely happy, but which at least allows to say, well, the image has halogen lights, a concrete floor, boxes, and many machines. Now, using background knowledge, semantic web tech, these objects are often present in and related to factory operations. The machine thus believes the image is of a factory scene. Why there's still a black box on here is that in the example where this is taken from, which you already saw the picture of Tarek at the start of the talk, which is work of Tarek Doran at Wright State University. What they're doing is they're training an image classifier. They have labeled inputs, outputs, and they're in parallel training a semantic net on recognizing which semantic labels from the input correspond to which semantic labels on the output, so that they basically in parallel train the semantics to the image classification network. Still, if you're interested in that, have a look at the website of Tarek Doran, Wright State University. And then, as I said, explanations are this warm, fuzzy thing. So what is an explanation? And with this, I will be done on the conceptual stuff, and we're looking at actual AI. Well, what people usually tell you is it's an explanation when it feels like one. So it takes away what's called the epistemic longing. You have the feeling that you got your answer answered. They should be truthful, and they should be complete. Quitting the epistemic longing is presumably necessary because otherwise you failed. Truthful is questionable because truthful also means completely accurate, and usually when you're explaining something to someone, you're leaving out details, you're generalizing. Think of Rutherford's atom model. So many people are taught in school that you have electrons in stable orbits around the nucleus. No. You have probability fields where electrons are theoretically somewhere and you never know where and all of that. Still, the nucleus and the electrons on stable orbit are truthful enough for most people. Complete, well, depends on the context. There are cases where out of mercy or compassion you actually might not even want to explain completely. So if you're looking at it from the AI side, tying back to Mickey, what they should be is probably communicatively effective. They should be accurate enough. They should be sufficiently truthful, and they should quit the epistemic longing. So these are the goalposts against which we are trying, or rather this bunch of merry people is trying to engineer explanations out of trained neural networks. Brief note to the backgrounds. Danny on the left originally was a computational neuroscientist. Daniele was a software engineering consultant. Roberto is a knowledge engineer. Yes, they still exist. And Sebastian is a physicist software engineer. So if you ever want to engage in this explanation stuff, I recommend you either, if you have the money, get yourself a team with this diverse setup, or make friends. But it's really helpful if you have someone who actually knows math, if you have someone who actually knows networks, if you have someone who actually knows how knowledge representation and ontologies work, and if you have someone who actually knows how to code. 4. And thanks to him, because most of the slides from here on I stole from him, as he's the actual master of how networks work. So, TREPAN. TREPAN, we'll come to it later why it's called the way it's called. Some native English speakers might know the word, at least if you're interested in medieval history. What TREPAN does is it takes a trained neural network and it extracts a decision tree from it. So most machine learning people now tell me, yeah, sure, you can always train a decision tree on data you use for training a neural network. Yes, but this is not what TREPAN is doing. TREPAN is actually training with the network as labeling oracle. So it's not learning from the data set, it's learning from what the network learned from the data set. And as we all know, there's a difference because otherwise you would have perfect classification. TREPAN tries to extract the rules the network learned, not the rules in the training set per se. It's also tech from the mid-90s. So Craven basically did his PhD thesis on it under supervision by Jude Chaflik, who back then was pretty big in tree-structured learning methods. There's a NIPS paper from 1996 where you have the gist of it. Trappin computes decision trees, arbitrarily approximating trained neural networks. What Craven and Chaflik did back then was using feed-forward nets because it's the mid-90s. Trappin is agnostic to the formalism. So there are a couple of requirements which you have to fulfill, but Trappin can, in theory, be used on whatever neural network. It's not limited to feed-forward nets. And Trappin is a knowledge extraction method, so you are not learning why a particular image was labeled as such or why a particular credit was rejected. What you are learning are the global rules the classifying network has learned. If you want to then know why a particular instance was classified the way it was, you can walk it through the resulting decision tree, but what you actually get is the tree approximating the network. So, simple example, which will serve as our working horse throughout the next, I guess, 20 minutes. Here you have a data set, and what you want to decide is, do you want to play tennis or not? So you get information on the outlook, on the temperature, on the humidity, and on the wind. Outlook, sunny, overcast, rain. Temperature, hot, mild, cool. Humidity, high, normal. Wind, weak or strong. I guess that's a UK data set because there is no humidity reduced. And then you play tennis or you don't, right? What Trappin now does is it induces a decision tree top-down. You start with the best attribute or the most informative attribute. If you would be doing this by hand, you go through the table and you'll figure that this most informative attribute actually is outlook. Why? Because there is one feature Outlook can have which classifies pure. So whenever the Outlook is overcast, you play tennis. Or at least from whomever you obtained that, whenever the Outlook was overcast, the person played tennis. If this would now cover the entire data set, you would be done, because then you would know, okay, I classify with my decision tree in Outlook overcast, yes, no, play, no play. Obviously, you're not done. So what do you usually do when something worked once, but you're not done yet? Reload and repeat. So within the Outlook attribute, there's two more values. One is sunny, one is rain. You have a look. Do they classify pure? No, they don't. So reload, repeat. Then you have a look at humidity and wind. And in the end, you get this decision tree. If you walk it through, it means that, okay, you start on Outlook. If it's overcast, you say play. If it's sunny, you have to look at the humidity. Outlook sunny, humidity high, no play. Outlook sunny, humidity normal, play. Outlook rain, wind strong, no play. Outlook rain, wind weak, play. These are the rules in the data set. Great, we have a decision tree. We managed to do something people managed to do for the last 50 years, but hey, it's a start. What I did not tell you is, for example, or what I did not properly tell you, is why we started on Outlook. Well, as I said, it classifies pure, but what does that mean? Then, why do we know that the training set we currently have is sufficiently pure? How do we know that the tree is actually good? There aren't any ANNs involved yet, but still I keep rambling about artificial neural networks, so what role do they actually play? And then, is this a unique decision tree? Let's go through these one by one. So, when I'm saying what attribute is best, and how can we tell whether the training set is sufficiently pure, and this is where the theoretical learning people's heart should now accelerate a little, you're actually looking at entropy or negative information in your training set. Because what you want to do, what does a binary decision tree do? It splits your data set at every step. And of course, you want to split it in a way so that you reduce entropy as fast as possible. So you want to be as efficient as possible in your splits. Which attributes do you use? Well, the attribute using higher information gain. negative information, it reduces uncertainty. It's considered the best, and the entropy measures the purity of the set. Formulae, yoo-hoo. You have your data set, and as I said, whenever you measure an attribute, if it's a binary one, it creates a subset as 1 and as 2 with different entropies. You can expand that. Conditional entropy is the mean of the entropy between the two sets. If you generalize this out, you just get the sum over the different values for the entropy values. And your expected reduction then, due to the partitioning, is the entropy of the overall set minus what you calculated before in the conditional entropy. You apply that over the training set, and this is actually where it comes up that outlook is the preferred starting point. So it's not arbitrary. It's not that someone sat down and had a look and, oh, there's 4 purely classifying ones. It's just the best informative one for your classification and the first step, reducing the follow-up sets. How do you then tell that a current training set is sufficiently pure? Well, you eventually get a pure leaf. So you reach a clear classification, and the pure leaf, the entropy is 0. There you stop splitting. So on this case, there would be no point in further pursuing, because if you would split further, all you get is further pure leaves. You can't do more than play on that point. Still, the ones for sunny and rain actually aren't pure yet, so there you keep splitting until you hit further entropy 0 points. So, and this is where it's getting cool. This far, it's still only decision trees, but this is where we now don't learn from the training set, but where we actually learn from whatever the network learned. Because instead of using the training set as labels, you actually only use it as input. You query the network on the instance you're currently looking at, and you're using the label the network returns to you. If the network perfectly reproduces the training set, that doesn't make a difference. But in most non-pathological or sandbox cases, of course, your network isn't classifying perfectly, and you actually want to know the classification rules of the network, not of the set. So whenever you're here having a look at your sets, you query the network, you don't look at the real label. So with the network as Oracle, you query it, you get the class as predicted by the network at each of the instances. In order actually to make it more efficient, you could also just do it for each instance, but then it gets a bit of a painstaking exercise. What you can do is that you can also just specify constraints on your feature values. So you give it a range. You don't only use the individual examples, but you say, okay, each feature value within the range of X to Y. TREPAN then randomly samples from these constraints. In the original mechanism, what they're doing is that they use frequency counts for discrete values, so you actually sample the distribution of the network. What you're doing for continuous features is that they use a kernel density estimation. This is the very original one. If you want to tweak it, there is things you can do. So if you happen to be into the mathsy side, not easy for a German native speaker to say. If you're into the mathsy side of the entire exercise, these sampling methods are easily tweakable. Also, if you're implementing them, there's some stuff you can do. But in summary, you're using the Oracle for determining the class labels for training examples. You're selecting splits for the tree's internal nodes, and to determine if a node covers instances of only one class. So, TREPAN, long story short, you get a decision tree from a network. Decision trees are presumably better readable representations. But TREPAN also is not only any decision tree. So if you're used to, probably you aren't, but if you would be used to using C4.5 or whatever else was fancy in decision trees in the 90s and partially still is, there are a couple of key differences. A, the use of the Oracle, because once again, I know I'm repeating myself, you want to learn what the network learned. You don't want to learn what's in the data set proper. You have a more smart tree expansion. You can play around with the split types. So what Craven and Shufflick back then also introduced is not splitting binary, or not splitting, let's say not splitting binary, but splitting M of n. So say you do not only have one condition in your decision node, but you have 20 potential features. M of n tells you go left if m of these n or more are met. In terms of thinking of M of n rules, it's a bit of a mindfuck, because it of course means that every subset of 3 or more fulfilled conditions lets you go left. But if you only meet 2 or less, you go right. Still, it makes the decision tree like you can fumble around with how deep, how broad, how shallow, how whatever you want your decision tree like that. Then the split selection, once again the oracle. And also what you can decide as a parameter is actually how many nodes you want. So you can set the depth of the tree as an additional parameter to the heuristics. That then also influences a little how closely you approximate the network in truth, because yes, decision trees are arbitrary function approximators as well as are neural networks. So if you give yourself infinitely much compute, infinitely much memory, and infinitely much whatever else you might need, you can approximate the network truthfully, but usually you don't have that. Bit of pseudocode, and since some of you are actually taking pictures, I guess these slides are being shared afterwards, right? Or at least there's, for all I know, there's a YouTube recording. So if you rather want to look at the slide than take the pictures, you can also just take a screenshot from YouTube later on. How do you do the thing? Well, you need the oracle, so you need a trained network, because that's the very meaning of the exercise. You have your training set S, you have a feature set F, then a couple of parameters and the stopping criteria you set. As I said, how many nodes, whatever else. And then you just go through the examples, you obtain the class labels from the oracle, you initialize the root of your tree, you construct the model of the distribution for the instances. Pretty quickly, you introduce a sorted queue of the nodes to be expanded. You expand the node, you make the children nodes, reload, repeat until you're through the set. Those of you who are thinking along in terms of how much compute that actually needs, in the worst case, a lot. Yes, like this is definitely not efficient in the classical sense of the word efficient. Still, you can limit the compute by the input parameters, trading it off against accuracy and approximating the network. Or you can just throw a lot of compute against it, and then you actually also make it into scales which are perfectly usable for practical examples. Thinking this a little further into, once again, Telefonica Innovation Alpha, you probably don't want to run that on the edge device. Notwithstanding the fact that your smartphone gets someone to the moon and back, you probably want to have that running on a little nice, well-cooled, high-performance computing engine. Incurs a bit more data traffic, but hey. Then how can you actually tell that the tree is good? Well, the tree is good if it approximates the network as well as possible. The property is called fidelity. How do you figure fidelity? Well, by having the tree classify stuff, by having the network classify stuff, and seeing how often they differ or not. If they don't, perfect fidelity. If they do, probably you're a bit more compute efficient. And is there a unique tree representation? No, not really. Yes, you do use, among others, entropy or negative information as heuristics. Still, you can restructure trees. They aren't unique. Does this have advantages if you're thinking back about what I ranted on regarding interpretability? Yes, presumably it has. There is not much, but a growing body of research on the more HCI side or on the more cognitive psychology side, where people are looking into, so now say I take a somewhat naive user and I present them a decision tree, how deep can I go without the user completely having no idea of what's happening? How broad can I go? How do I split? So can I actually use M of n rules, or do I have to enforce either 1 of n? So in this case, I have an or between all the feature, or n of n, which means I have a complete conjunction. All of these are parameters you can set. So then, why is the thing called trepanning? Because trepanning was an appreciated technique in the mid-ages to try to cure headache, namely by drilling a little hole in the skull and allowing the brain and the built-up tension to escape. So what you're watching in the middle is a trepanning procedure. What Trappin in its original form, and as it's been used until now, if it's been used, is doing is it's extracting a decision tree using the original input features. And I said there's a knowledge engineer on my team, or on this part of our team. What we are currently looking into is, okay, but do we really have to use the sometimes arbitrary input features, or can we maybe back this up with a background domain ontology? So can we actually just say, well, there are these 3 input features which when taken together describe a person's fitness habit, or do they like pizza, or what have you? Answer is yes, you can. Challenge is, of course, when you're drawing together features, this basically means you're messing around with your pre-selected entropy or with some other criteria. So you're messing around with the statistics. It might come at the cost of not being able to sample the actual distributions of the network anymore as well as you originally did if you try to bake it into the very algorithm. Or what you can also do, and what's the quicker way in, you extract one of these trees, and then after having extracted the actual tree with high fidelity, you restructure it. So you take the output of Trappin and you try to map the output into a decision tree which has as high fidelity to that one as possible. Still, also there, you're losing on classification accuracy if you would run it on the original data set. Nonetheless, it might be worth it because then maybe people understand actually what you're telling them. Also, I already said that Trappin is agnostic to the types of neural networks you use. And in theory, it can be applied whenever you can come up with means of conditionally sampling your input space. What we are now looking at is, okay, on feed-forward neural networks, Craven got a PhD degree for that, and people reproduced it many times. That probably works. What happens if we extend that to RNNs? The simplest way of doing that would be to unroll the RNN in time, so to basically junk it into a succession of feed-forward neural networks. Once you've done that, you can just run it through your original Trappin algorithm. The problem you're having is that you have no idea of what the meaning of the output is, because you actually are losing the entire temporal dynamics of sorts. So is it meaningful to straightforward apply Trappin to an RNN just because you can do it in that way? Presumably not. Can we come up with a smarter way of getting actual trees out of RNNs which somehow take into account temporal dynamics? That might be a NIPS 2019 paper if anyone feels like it. Also, as I said, what makes decision trees understandable in the first place? Just throwing a tree at someone clearly doesn't solve it, but what are the things that you have to take into account? And then, 2 years ago by now, Nick Frost and Jeff Hinton published a paper in which they introduced soft decision trees for convolutional neural networks. Soft decision trees are completely different in nature, most likely, in that they rather are probabilistic and that the entire mechanism works differently. Nonetheless, several people hold the strong belief that there should be a commonality between trees extracted with Trappin-like formalisms and what Nick and Jeff were doing there for convolutional neural nets. This is an open question. Like, we don't have any idea yet. We're playing around with it. The soft decision trees have their strength in certain applications, not so in others. Trappin also has its strength in certain applications, not so in others. But if there is a connection, and if so, what is this connection? Not entirely clear. And yeah, then there is many more other questions. So what types of decision trees are best suitable for extraction? Are there maybe other ways of extracting them in the first place? Can it be more efficient? There's a lot to tweak, and was in the 90s, so it's actually fun to read that NIP's 1996 paper, as Craven has this initial paragraph where he's like, yeah, it's fairly common to extract decision trees from neural networks. There's this body of algorithms. This one is more general. If any of you finds an opening paragraph of a machine learning paper from the 20 years after, where someone says it's totally common to extract rules from neural networks, please send it to me. Which brings us, and this is now the hopefully morally uplifting conclusion of my sermon, which brings us to a more general question, namely knowledge extraction from networks, or the other way around, encoding knowledge into networks. If it is really true that symbolic representations are better suitable for being interpreted or for giving rise to explanations, then maybe we should just go back to a research endeavor which has been lingering in the background for quite a while now, either called neural symbolic integration or knowledge extraction and injection, or you name it. But technically, at least if Hannes Leitgeb and quite a bunch of other people in the, once again, early 90s were right, it should be possible to represent and, yeah, well, if they were right, then there is no fundamental difference in representational and computational capacity between certain symbolic representations, non-monotonic logics, and any kind of statistical method which can be depicted as a dynamical system. And this maps pretty much the entire space. There's a couple of outliers there, and there's a couple of things where people dabble around with going super Turing, but leaving the odd corners of esoteric theoretical computer science aside, there is no good reason to believe why it's fundamentally impossible to extract knowledge from networks or to encode it. We just have been failing for the last, and if you take 1956 as a starting point, for the last 62 years. Question being why? Well, maybe there's a huge computational overhead, or maybe we're thinking in the wrong direction. Still, might be worth looking into, and people now actually start doing it. So there are a couple of highly performant systems developed by a Google subsidiary in this city, which pleasantly combines cutting-edge machine learning with search trees and the like. There are quite some attempts when you're looking at using machine learning for actual scientific purposes, so doing huge data-driven applications where you want to extract governing rules or laws for domains. People are starting to walk in that direction, but still, it might be one of the steps beyond deep learning, unless you follow Jan LeCun's Twitter stream. He is always of a bit of a different opinion there. So, end of the sermon. Final advertisement teaser. Alpha Health AI Lab, we're around. We try to do things like trustworthy AI, empathic AI, privacy-preserving AI. I've been told that at the end of this, people can walk up here and do 30 seconds of job announcements. So if you actually happen to have credentials and at night dream up homomorphisms, or are really one of the core contributors of the open mind community and are not called Andrew Trask, or really always wanted to explain to me how to build an encrypted enclave in which to train your networks without seeing the data, this is the email address. We are very happy about anyone who actually has an idea for how to properly do that. And otherwise, so one of the original plans of giving this talk today was to release a open source version of our Trappin implementation, which cost one of my guys quite some nerves porting it from non-compiling mid-90s C to nifty C++ and equipping it with a couple of interfaces to TensorFlow, PyTorch, you name it. But unfortunately, there are a couple of final 100 lines of code which give us a bit to think. So follow that Twitter account. There will be an announcement soon with a GitHub repository where you can just download all I told you about now and can play around with it soon, meaning 2 to 3 weeks from now if everything goes well. So, according to the official schedule, it's time for beer and pizza. If you have questions, comments, but keep in mind, you're standing between people and beer.
Okay, I'll make it quick. Actually, unfortunately, my question has an assumption. So I didn't quite understand. Do you have one tree per model, or do you have a different tree for every example you're trying to explain?
One tree per network. One tree per trained network.
Right. Okay. So essentially, this is something that's part of learning and not inference.
Yeah.
So my question is, first of all, if you're going to use this to provide this explanatory power for the GDPR purposes, then by surrendering that tree, you're going to be giving up a large part of your algorithm. You're going to be giving up an algorithm that will explain 90–80% of your explanatory power of your core algorithm. Secondly, why not actually? Why not do a new model for every example? Because then you can go down the path that led to the explanation of that example, and you can go deeper into the tree, and half of it is irrelevant because it wasn't overcast on that day, it was actually raining.
I think the first one didn't feature a question mark, but my internal classifier claims. But yes, first one, point well taken. Second one, also point well taken. The point of the exercise, in a way, is to give a truthful global depiction of what the model is doing. So in terms of global category, this falls into, or in terms of general category, this falls into global model explanation. But yes, your intuition about the samples is right. And you could just as well do that. Yeah. I think the answer is yes. Yeah.
So two questions. The first one is that if you were to take the TREPAN drive model and re-implement it, would it be quicker than many of the CNNs that are developed? Because they tend to be quite slow and resource intensive. And the second question is, do you envisage a future where, for example, legal teams would use a TREPAN or similar methods to take the models used by a company and realize whether the model is voluntarily or involuntarily using features that are illegal to use, such as skin color, gender?
First one, so as I said, for CNNs there isn't a TREPAN yet, but in theory there should be one if someone figures how to do the sampling and stuff right. But yes, it should be faster. So what is one possible rationale one can give for this exercise is that the network's presumably trained better, but the tree classifies faster. So if you can afford to train a network, extract the tree, which is computationally costly and takes time, but then run the tree, that should buy you time on the classification. Problem you're running into is when you're, for example, having an application where you train your network continuously or where you retrain it very often because you have to extract a new tree every time. So this is application dependent, and as I said, if then you're talking about edge devices, you have to shift, well, you might actually be possible to still train a CNN on a edge device. It's a bit of a stretch, but hey. But the extraction and stuff you have to do server-sided. And the second one, yes, this might be an application case where rule extraction in general and TREPAN being one of the, in my opinion, more promising approaches could find application. The ramifications this has in terms of cultural values within legal teams is that, and there's also a hypothesis here, if AI becomes as ubiquitous as many people currently assume, in a legal team you will just need someone who understands the tech and who can, for example, run things like these. But yeah, like this is one of the, so if you were to start a venture in explainability, and you would go to insurances, to legal consultancies, to auditing firms, I don't think you would necessarily be walking in the wrong direction for capital funding. Just saying.
Maybe one more question?
Gentleman in the back.
Hi, thanks for the talk. So I'm just kind of curious, I know you've touched on this a few times, but with regards to applying TREPAN to CNN, you mentioned, okay, it's a question of the sample. But maybe I'm lacking a bit of imagination here, but I just wondered whether you'd be a bit more specific as to, you know, I mean, in the toy example you gave in the course, the features, the input features themselves were already quite high level, right?
Yeah,
so
sure.
in that kind of circumstance, it's very
Yeah.
easy to see how, given a decision tree, you can then interpret the output network. But then rewinding perhaps to some of the examples you gave at the beginning of the talk, where you were like, okay, this dog was mistaken for
Yeah. Yeah. No, you're spot on. Yeah.
Can you elaborate a little bit on what your thoughts are?
I see where you're going, and you're spot on. So I don't know whether Roberto actually did that, but he basically started exactly on that point a couple of months ago, where he was like, yeah, so if we do image classification, Trappin is going to be able to tell us that pixel 27319 was like this, and then we're going there, yeah, no point in that application to run it in this version. So what you might be able to do though, and this is either pre-processing or modifying the internals of the algorithm, is first push it through a image labeling network and then see whether you can train a network which classifies the images the same way as the original one did, but based on the labels, and then extract the rules from that one. Still, there's this intermediate step where you basically introduce the high-level categories you rightfully pointed out in the toy example.
So this is going down the direction of basically having attributes.
Yeah, exactly. Unless, post-processing-wise, you somehow manage to relate pixel 13, 257 and pixel 918, 1050 in an explanation. So if you can post-hoc do that by whatever magic trick, this is also working, but yeah, TREPAN to be reasonably usable in interpretation and explanation needs attributes. Touché.
We